And then 10,000 years later, you'll have 8 or 9 more days of winter, depending upon whether you're tilted towards the sun in the northern hemisphere or else tilted away. So it's a very slight effect. But it's important for all of these effects to operate synchronously. So what my coworkers Norton Wong and Zahua Wu and I have done are take these ice core data, and these are the temperature data, and then we decompose them by this nonlinear, non-stationary time series technique called the Hilbert-Wong transformation. This is an adaptive technique, and you break out into different periodicities various components in the core. The same technique is used to filter digital telephone calls and conversations. So now we're looking at some of the components of this decomposition which have longer periodicities. So for example, what I've labeled as C9 has about a 21 or 22 or 23,000 year periodicity, C10 about 40,000 years, and C11 about 100,000 years. Now the core is only 440,000 years old, so you can't study a 400,000 year cycle when you only have one cycle. So therefore, what I'll show you now will be reconstructions using these components, which correspond almost exactly to the periodicity, or the shorter periodicity for eccentricity and the periodicities for the obliquity and also precession of the equinoxes. So when we do this just for the 100,000 year periodicity, we also include these longer periodicities, but again, the core is only 440,000 years, so this doesn't really contribute to it. And the red line is how well you do when you superimpose these data upon the actual data which you got from the core, from your 018, 016 temperature reconstruction. And so you see that you match up fairly well like this, but you could do a lot better. So this is just the eccentricity component. Now let's add obliquity to it. And you see you do better. So now we're looking at periodicities that are superimposed to explain the variation, only looking at these periodicities of 40,000 years, 100,000 years from eccentricity. And when we add the precession of the equinoxes, then we match up very well. So what this says, and other people have done similar work using different techniques, is that orbital dynamics explain what sets off and what brings us out of ice ages. Now, what about all the other variation? Well, it's here. And so what's represented here in red are shorter term variations of the Earth climate system, which have periodicities from several hundreds of years to 10,000 years. And so you can view this in a sense of being analogous to the difference between weather and climate. The ice ages and the interglacial periods would be climate, as you come down like this, and this would be all of the shorter frequency variation like weather. And so here we're talking about what forces the climate. Now let's look and see how much energy is involved in this orbital forcing of the Earth system. From our analysis of this, we conclude that eccentricity, obliquity, and precession explain about 57% of the total variation of these data in a variance sense. And this results in an orbital forcing of about 0.3 to 0.5 watts per square meter. So that's very, very small if you consider the energy from the sun at the top of the atmosphere is about 1361 watts per square meter. But what happens is this sets in motion feedback mechanisms which involve the greenhouse gases and ice on land that reflects light back into space, and that then contributes to a plus or minus 3 watt per square meter supplemental effect after things are set in motion by the orbital dynamics. So if we look here, I've just brought down 2 lines which show you what the variation is at the top of this graph in terms of the atmospheric carbon dioxide concentration from the ice core data. And this varies from about 180 parts per million at the glacial maxima to about 280 parts per million in the interglacials. So now what Jim Hansen has done with 1 or 2 of his coworkers is they've calculated what the forcing is of the variation in carbon dioxide and also methane, and then they have computed that in energy terms. But first they wanted to see if temperature led the greenhouse gas concentration or if the greenhouse gas concentration led temperature. And historically, what they found was that temperature set in motion these feedback mechanisms of greenhouse gas concentration by something on the order of approximately 700 years. That's now been refined to about 500 years when you have better data, because all the time our ice core people are working to better date the core. So what's represented here in the bottom graph is the forcing which results from the greenhouse gases of carbon dioxide, also methane, and this is then plotted against the Vostok ice core temperature in green, and you notice a fairly good match. But there is this offset of several hundred years, so you've had to slide the greenhouse gas forcing data to coincide then by 700 years. Now, what do you do about the albedo feedback? Well, you can look at sea level variations over time, and then you can take the cube root of the square of the volume of water, which has been evaporated from the oceans, and that is a good approximation for the area of ice on land. And ice is very reflective. Ice and snow are very reflective, as we know, and they reflect back probably 80 to 90% of the downwelling radiation from the sun. And so from that, you can calculate by what the ice extent is, how much that is a greenhouse gas or what the albedo forcing is in addition to the greenhouse gas forcing. So in this figure, and again, if you're curious, please look at the materials. Here we have at the top 3 sources of sea level variation over 440,000 years. Here we have this calculation of the energetic forcing in terms of surface albedo and greenhouse gases. And so for both of them, it's on the order of from 0 to 3 watts per square meter. And then again, here's this overplot showing how well they agree with temperature when you adjust for the 700-year lag period. So what this says is our climate has been very stable, and only a slight forcing can force us into an ice age or bring us out of an ice age. And this results completely from our study of ice cores. So the summary of this is we conclude that our climate system is very stable and has been remarkably stable, at least for the past 1 or 2 million years, that the glacial onset and the interglacials are set in motion by orbital dynamics. These 3 orbital dynamics which interact with these periodicities of about 100,000 years. And these result in a very small forcing on our climate system of 0.3 to 0.5 watts per square meter. There are then set in motion feedbacks from the carbon cycle and the greenhouse gases, as well as albedo, which then push us into and bring us out of these glacial, interglacial cycles. There are lags in the system because of oceanic processes, and all this is related to temperature, surface albedo, and sea level. And therefore, greenhouse gas emissions could put us in the danger zone and force us even further. Furthermore, there is evidence of geological sources which indicates that CO2 concentrations greater than 500 parts per million, whenever they've occurred historically, we have lived in an ice-free world, which means the sea level would be about 100 meters higher than it is now. So let's look briefly at some carbon dioxide data, and then I'll conclude with some things we can do so we don't leave here depressed. So these are some data showing what the atmospheric CO2 concentration has been over the past 10,000 years, from then until now, based upon ice core data from Greenland. And you see that we come along and then things shoot up. And then we have the inset of data from the late 1700s through the present, where you can see what composes this vertical line at the bottom. Now, it's very fitting that we're here because a very famous Swede was responsible for first elucidating that our accumulating use of the carbon dioxide from the use of fossil fuels was accumulating in the atmosphere. This was Professor Arrhenius, who is extremely well known. In the lower right-hand corner, I have pictures of Dave Keeling, first as a graduate student, and then as he was before he passed on a few years ago, unfortunately. And Dave Keeling started measuring in the late 1950s on top of the Mauna Loa volcano the concentration of carbon dioxide in the atmosphere day after day after day. Now, in my career, I was fortunate enough to work with Dave Keeling on 4 or 5 journal articles, and he was the most compulsive person I've ever worked with. he would fight to be the second or the third author on a paper by doing more work. If you did any study, he would come back and say, now, okay, do it again. We have to get this right and make sure there's no ambiguity, that there's no error. And because he was so compulsive, it's why we have such excellent data of his, of the atmospheric greenhouse gas concentration. And you see this varies month by month. When it tends to increase, we have the northern hemisphere winter, when land photosynthesis is shut off. The secular increase is because we're burning fossil fuels. But this oscillates around these increases. Then when the northern hemisphere winter comes, and in say July or August, then you have a lot of plants that are photosynthesizing, so they suck carbon dioxide out of the atmosphere, and you come down, and you start back up again. We're burning fossil fuels, and so we have an increase of CO2 in the atmosphere on the order of 1 or 2 or more parts per million per year. At the same time, we have an accumulation of carbon dioxide from fossil fuel use in the atmosphere. We also have an accumulation of PCO2 in oceans because of the simple diffusion from the atmosphere into oceans. That is shown in the blue figures on the right-hand side of this, on the dark blue figures. And this results in an increase in the acidification of oceans. That is shown in the light blue. So here we have the increasing atmospheric carbon dioxide concentration. Here we have the corresponding increase in PCO2 in the oceans, also going up, and this translates into this decrease in pH, which you see here, which is the consequence of more carbon dioxide in the oceans. This contributes to ocean acidification. This is referred to as global warming's evil twin. In the supplemental materials, I have 10 or maybe 9 slides on this topic. These are some slides which Richard Freely let me use in presentations like this. If you're interested in anything about the oceans and ocean acidification, you should look at the supplemental materials. Now, how long does carbon dioxide remain in the atmosphere? Well, a portion of it remains for a very, very long time. That after a millennium, 1,000 years, just under 20% remains in the atmosphere. After 100 years, about a third of it remains. And of course, the difference is there's a very fast removal of part of it, but a large quantity of what we emit today will be in the atmosphere long after we are gone. So what do? Well, if we keep going the way we're going to increase the atmospheric carbon dioxide concentration somewhere in the order of above 600 parts per million. And that's largely through the use of coal. Oil and gas are only a minor problem, and then deforestation, which is in the green zone on top of these curves, is the consequence of cutting down forests and then either the decomposition of those forests or of the burning of them. Now, when we're talking about fossil fuels, it's important to look per unit of heat how much carbon dioxide is produced. For natural gas, we're in fairly good shape because natural gas is a very clean fuel. Petroleum has about 50% more carbon dioxide for the same amount of heat released. Coal is about twice that of natural gas, but tar sands are 3 times, and oil shale are slightly more than 4 times. And that's because if you want to combust a fossil fuel, you need to get it into a gaseous form. And if you go from a solid to a liquid to a gas, that requires energy. That's 2 phase changes. It's even worse for tar sands and oil shale than it is for coal. In many places in the world, like this is a photograph from Wyoming in the United States, you have these massive coal seams. But what's happened in the US, and then here's one of these coal trains coming out of Wyoming, they're long, and you never want to be someplace where one of these comes by without an overpass, because you can be stuck there for a hell of a long time. But what is happening now in the US is we've found huge reservoirs of natural gas. And one large formation which runs all the way from Kentucky up into New York State, there's also natural gas which has been found in parts of the western United States and also in North Dakota. And so what we have to do, in my opinion, and Jim Hansen's opinion, and many other people, is we have to minimize our use of coal. So we can do that, and if we do that, we can stabilize the atmospheric carbon dioxide concentration somewhere above 400 parts per million, and then it will gradually reduce over time. And what is happening in the United States now is that a huge degree of our electrical power generation, which formerly came from coal, has been replaced by natural gas. This is a figure from the July 2010 issue of Scientific American. And this is one of the reasons that I'm encouraged that in some place like Texas, which doesn't have a very high environmental awareness, now 99.5% of the electricity generated in Texas comes from natural gas. So in all of these blue areas, it's extremely high. Also in Florida, also in this part of New England, and we have to work on this area in Illinois, in Ohio, and in the upper Midwest, where still about half of their electricity comes from burning coal. But unless there's an intervention to make coal really, really cheap through subsidies, natural market forces will replace coal with natural gas. Because the price of natural gas in the United States has fallen from about $13 or $14 per thousand cubic feet 3 years ago to under $4 per thousand cubic feet now. Okay, so what our target should be in terms of atmospheric carbon dioxide concentration, because this is a greenhouse gas forcing, is somewhere on the order, most of us think of around 350 parts per million, which we passed about 15 years ago. But if we have intelligent use of fossil fuels, we can come back to that point. So I'll conclude here, and this is a picture which I like to show during the time of George Bush and Dick Cheney, people at the White House in Washington, D.C. On the left-hand side, you see the obelisk, which is the Washington Monument. Also through the window is the U.S. Capitol building. And so I imagine this was Dick Cheney, who we thought was Darth Vader, sitting at his table, and he's talking to some of his colleagues, and sea level rise has come, and they're finally saying, ladies and gentlemen, it's time we gave some serious thought to the effects of global warming. So thank you for your attention. Again, anyone who wants this presentation is welcome to it, as well as supplemental materials. There's a lot more information on many of the areas which I touched upon. And I only ask you, if you find any mistakes, to please communicate those with me. I'll be happy to answer any questions, and thank you for your attention.